So boys and girls, now we are going to talk about the pressure of gas on basis of kinetic theory of gases. So according to the kinetic theory of gases, gas pressure is the result of collisions of large numbers of molecules on the wall of the container. So because of the gas molecule keep on collide with the wall of the container, they are doing the elastic collision with the wall. That's why we create gas pressure. So as the gas molecule collide with the wall of the container, it will change directions. So when this happens, the molecule actually exert force on the wall of the container. If you still remember in chapter 3, when we have collisions, during the collision, we are going to have what we call impulsive force. Boys and girls, recall what we learned in chapter 3. So when during the collisions, when the gas molecule collide with the wall of the container, it exerts what we call as impulsive force on the wall of the container. So refer to the basic definition of pressure. Pressure is the force over area. So the impulsive force during the collisions divided by the area of the wall container, we are going to get what we call pressure. So the force exerted over a unit area by all gas molecules as they hitting the wall of the container around them will produce what we call pressure. So in a simple way, we might say that gas pressure is due to the collisions of the large numbers of molecules with the wall of the container. So during collision, they have impulsive force. This impulsive force divided by the unit area of the wall container. So we obtain what we call pressure. Alright. So class, the pressure of the gas can relate with the roof mean square speed of the gas. You can see very obviously from the previous diagram. Only when the gas move randomly and keep on collide with the wall of the container, we create pressure. So we might relate the pressure with the roof mean square speed of the gas. This is the equation that we relate both of them. So we have PV equal to 1 over 3 mn roof mean square speed squared. We rearrange the equation. We move the volume to the right hand side. So we have pressure is 1 over 3 and mn vrms squared over v. Then class, the mass of a molecule gas multiplied with the total number of molecule gas, we will get what we call total mass of the gas. This one will represent the total mass of gas. So, total mass of gas divided by the volume. V is referred to volume of the gas. So, if we recall our prior knowledge, that one will represent density. Density of a gas. So, total mass divided by volume. Mass divided by volume, that one is density. So, I replace it into the above equations. So, I will get another equations. Pressure is equal to 1 over 3 multiplied the density of the gas multiplied with the roof mean square speed squared. Okay, so this is the two equations that relate pressure with the roof mean square speed of the gas. So from this equation, we can obtain a very important result that we managed to relate the macroscopic quantity pressure to the microscopic quantity, the roof mean square molecular speed. So we have established a key link between the molecular world and the large scale world lah. So kita berjaya untuk relate kan, sebenarnya pressure tu adalah disebabkan oleh pergerakan, velocity, the speed of the movement of the gas. Okay. So this is how we relate the macroscopic scale with the microscopic scale. Alright. Then class, we might also relate the roof mean square speed of gas molecule with temperature. So from the ideal gas equation, PV equal to NKT. Then just now, we have another equation for PV. So we compare it with this one. PV is 1 over 3 mn vrms squared. So equalize these two terms. Samakan dua-dua ni. Equalkan dua-dua ni. So NKT will equal to 1 over 3 mn vrms squared. So the n can be cancelled. Rearrange the equations. So I will get the roof mean square speed vrms squared equal to 3 kT over m. So squared, I square root both sides, so I get the equation that relate roof mean square speed of the gas molecule with temperature. We have vrms equal to square root of 3 kT over m. Okay, then class, from previous lesson, we know that the K is the Boltzmann constant, whereby Boltzmann constant is the molar gas constant over Avogadro number. So I put this one into this equation. So I'm going to have vrms equal to square root 3 RT over M and A. And then class, this M and A actually is equal to molar mass of a gas. Molar mass of a gas. I might have this equation, vrms equal to square root 3 RT over M. So the mass multiply Avogadro number, we get molar mass, M, capital M. Alright, so this is the two equations that relate the roof mean square speed for a gas molecule with the temperature. So the small m represent the mass for a molecule. Be aware, it's just a molecule, one molecule gas. Capital M represent the molar mass of the gas in kg per mole. T represent the absolute temperature, unit in Kelvin. K is the Boltzmann constant. So the R is the molar gas constant. These two equations, we can see very obviously our roof mean square speed vrms is directly proportional to the square root of absolute temperature and inversely proportional to the square root of molar mass of the gas. It means that the RMS speed of gas molecule will increase with the increasing of temperature, because we said vrms is directly proportional to the temperature. And for a given temperature, we find out that the lighter molecule will move faster on average compared with the heavier one. Why? Because the vrms is inversely proportional to the molar mass of the gas. So on average, you will find out that the nitrogen molecule 28 gram per mole in the air around us are moving faster if we compare with the oxygen's molecule, which have a molar mass of 32 gram per mole. Hydrogen molecule with molar mass of 2 gram per mole are the fastest of all because it's the lightest. Okay, so here is the table that shows us the molar mass and the vrms for some of the gases. So class, using this simulation, let us see what happened to the roof mean square speed of the gas when the temperature increases. See, when I heat up the container, the temperature increase, and you will see obviously the gas is moving faster. So their vrms is crater. And then I decrease the temperature. See, I decrease the temperature. Observe what happened to the movement of the gas. Observe what happened to the movement of the gas. You will find out that when temperature drop, the gas becomes slower. They move slower. Dia gerak dengan lebih perlahan. Okay. So this is the relation between the roof mean square speed of the gas with the temperature. Let's see another one, how the roof mean square speed of the gas relate with the molar mass of the gas. Okay, so the blue color is the heavier gas. Then I try to put in some lighter molecule gas. You observe and distinguish their movement. See? The smaller or lighter particles, the gas molecule, they will move with a greater roof mean square speed compared with the heavier particles or heavier gas molecule. Alright, so from this simulation, we can see very obviously our roof mean square speed of the gas depends on temperature and also the molar mass of the gas. So class, now let us try tutorial 13, question 5 and 6a. See how we are going to apply the concept on the roof mean square speed of the gas and also the pressure